Hello, girls and boys. Now it's time. Let's begin. My lecture is Introduction to Information Retrieval. Nowadays, we are in the information society, and most people get information from the website. But in the old days, people get information just person to person. Maybe some people travel to another place to meet the people, get the information, and nowadays the world changed. So get the information is very important, especially for the searcher, for the scientists, and for the scholars. The information retrieval is also very important to the medical students like you. If you want to be an excellent, talent doctor in the future, you must learn how to get the best information and the most advanced information. And the method of it are very important. So let's have a journey to see of the information retrieval. Now, let's begin. Information retrieval. What is the information retrieval? The definition is like this. Information retrieval is finding materials of unstructured nature that satisfy an information need for within large collection. Now, you should know what is the unstructured and what is the structure. What's the difference between them? I'll tell you. These days, I tell you later. These days, we frequently think first of web search, but there are many other cases, such like email search on your computer, and searching your laptop, and the corporate knowledge bases, legal information retrieval, something like this. It's different from web search, and I'll tell you in detail. Now let's see this picture. This is the model of information retrieval system. First, let's see this metadata means database, and the database get the content. The content, we put the content in the database, but not originally the documents or text we put it in the database. That's wrong. We should make it indexing. Later I tell you what is the indexing, and then you can use search engine get information from the database. You give the query on the search engine, then the search engine return back some information from the database. But some people don't use the platform such like search engine. They directly use the database. They get the especially the professional persons for the database. They get the information. They put the query directly from the database. Here we call it the metadata. The retrieval. They get the information what they needed. These people are very professional. They use a professional method, but the common people, they use a search engine. It's necessary for them to use the very special professional method. If you use the query directly from the database, you must learn how to operate the database, and it's a professional training about it. It's not easy to do that. So there are two methods. Now you can see there are two methods to get information. One is from the search engine, usually on the website from the search engine. That's very easy. And the other method is directly from the database. You use query just from the database directly get the information. These two methods for the people, but for professional people, you should use the query. And later I tell you how to use these two different methods. The most importantly, I tell you why we use the query directly from the database and use some logic operators such like and or not. I tell you in details. Let's first see the unstructured and the structured that in the mid-90s, from 1990 to 1999. In this period, you can see that this means unstructured data, like this one, the data unstructured, the blue color, and the structured, the black one. And in the old days, the unstructured text much more than the structured. But later, in the Word, the unstructured documents much more than the structured. But in the market field for business, you see mostly the structured occupied the bigger part of the information. Why it like this? I tell you next page. So you see, but nowadays the word changed. The text unstructured and the structured. Unstructured sort up very quickly. Now you can see this is the unstructured, and the structured not much more. But in the market field, the structured is still occupy a bigger part, but compared to the unstructured, it's less than that. Let's have a basic assumption of information retrieval. The collection, a set of documents, assume it's a static collection for the moment. That's a static. If we get a set of documents, we just give an assumption that it's a static, not a dynamic collection. For the moment you use it, and the goal will retrieve documents from the information that is relevant to the user's information need and helps the user complete a task. Relevant means you concern about it. It's satisfy your need. And let's see the classical search model for it. Now you still pay attention to the database. Here we use the collection. In fact, it's a database. So the common people get a database from search engine. The documents return back from the search engine, and if you This is the user. User have the task and then translate the task to your need. Then you use the query put in the search engine to get the information. Retrieve from here from the database. The database return back the information to the search engine. Then you get it. But first, you should in your brain. You should have an idea. That means you have the task. Then the task you make your task become the make it as your information need. But you cannot directly put the information need on the search engine. Maybe it's too long. So you make it just a symbol with some keywords or terms. Put it in the query to get it, and maybe you, with the different queries, the search engine return back not the same information. If you give the best query, you get more information that you need. If the query is poor, not so good, you put it. You type it on the search engine, maybe you get the information is not you need. And this is just like nowadays you use the ChatGPT. When you use the ChatGPT, you also first you have the task. Then you make the task as a prompt. You put the prompt in the ChatGPT dialog box. Then you get the result, what you need. The important thing is that the prompt is good or poor. It's strong or weak. Just like that, you should use the good query. And to the ChatGPT, you should use the good prompt, not the poor prompt, so you get the information back what you need. When the search engine, if the search engine return back the information not good, the results not satisfy you, maybe you refine, you change your query, then you put the query to the search engine again. You prove it, then maybe the return back, the information return back is better than last time. So this is just the circle. This circle, how you refine, you improve your query. Just like in the ChatGPT, you improve your prompt. The same. The most important is the collection. The collection, in fact, it's a database. And let's see. If you want to, for example, if you want to get rid of mice in the politically correct way, be careful. You should use the political correct way. So this is your task. And you would like to make your task as a need. Now see the info about removing mice without killing them. That means without killing them. That means politically correct way. And this is for the info need, for the information need. The get rid of mice just the user's task, and you make it as your info need, the next step. And then you should think how to trap the mice alive. So you trap it alive, that means you without killing them. So this is the good query. How trap mice alive. This is the good query. So the good query will get the result what you just want. If you put the wrong query, just like you just mean get rid of mice or removing mice. Maybe you get the result is correctly, politically correct, not a correct way. Maybe the result is how to kill the mouse, or that is not you wanted. So you should make the good query. So you should not the first step. You should not miss conception. The next, you should not miss formulation. With these three steps, you improve your you put in your correct query. Your correct query, also we call it the strong query, not weak query. The correct query. The correct query will get the correct result, what you wanted. So this circle is just improve your query. When you use the search engine, you should consider your query, consider it, think it over and over, and then you can get the information from the database what you want. From this, you also know how to use the ChatGPT. You should put the correct prompt. Some people nowadays, always ask me, the ChatGPT is not good, they said, because it always give me a wrong answer, a wrong result. I tell them, that's not the fault of ChatGPT, that's the fault of yours, because you put the wrong prompt, not a good prompt. So the ChatGPT don't understand what you really want. So you should when you put a prompt, you should think it over and over. And when you use your query, you also think it over. Not put the wrong query. Okay. Let's see the next. How good are the retrieval documents? And how we evaluate the search engine? What kind of the search engine is good? What kind of search engine not so good? How evaluate these two? We have these two target. One is the precision. That means the fraction of the retrieved documents that are relevant to users' information need. If the fraction is bigger, that means the precision is good. And in opposite, the precision, if the fraction is small, the precision is not so good. And the other is recall. The search engine's recall. This is the fraction of relevant documents in collection that are retrieved. Okay, and more precision definitions and measures. Let's follow later. And if I give you a picture of this, you can understand these words, this sentence quite good. So I give you a picture like this. What is precision? Precision means the relevant documents, the relevant documents over relevant plus unrelevant. That's relevant means that's the information, the brown one. That's the information you wanted. Unrelevant, that means the information you don't want, you don't need. So this is the the documents. This is the database. We get the retrieval returned result like this, like a cup. This is the bucket, a cup of water from the bucket, and the brown one, the brown part to the whole cup of the water. That's the precision. That's the precision. That means the precision of the search engine. These two means the search engine's quality. The quality of the search engine is it's a good search engine and a bad search engine. If the precision is good, that means the search engine is good. But also there are another condition that the recall. Recall means you get the relevant in the cup, the brown one, and the whole brown one in the database compared to it. The recall over relevant to the relevant total. This means the recall. Now you see as the precision is the relevant part over the relevant part plus unrelevant part on the retrieval information or in the total cup. It's non-business to the database. Non-business. Just compare in this cup, the water in this cup. That means precision. And the recall means the relevant just in the cup, the brown one, to the bucket brown one. This is over the relevant total. That's the recall. Under this, if these two conditions are good, so that's the good search engine. These two, the position and the recall, just the standard of the search engine. Whether it's good or bad, you use this like a standard for the search engine. We also call it the search engine evaluation. Okay. Then from this you can see, from this picture you can see the graphical depiction of the element necessary to calculate recall and precision. If all the database like the big one, and the number two is retrieval. Number two is the retrieval, and number three is relevant. Retrieval and relevant. Number one is the retrieved and relevant. If the number one over number two, number one plus number two, that means decision. If the number one, if relevant and the retrieval, you can see the table like this, and just think it precision is retrieval, retrieval relevant over the relevant, retrieval the relevant. Okay, and let's see the next unstructured data in 1620. Let's give an example. What means unstructured and structured? Let's give you an example. Then you can understand it quite well. Unstructured data and structured data. Let's give you an example. Which plays of Shakespeare contain the words Brutus and Caesar, but not Campania? And Shakespeare's play is a big thick book, and with several parts. And Brutus is a character of the is a person character of the in the story, the person of the story. And Caesar is the emperor, Roman emperor. And Campania is the wife of Caesar, she is the queen. And the Brutus is Roman emperor's autocratic, who's official, who murdered the Caesar. And if the people ask you which plays of Shakespeare contain the words Brutus and Caesar, but not Campania, which players of Shakespeare? And one could how you in the Shakespeare's he has many players. Which player have the words Brutus? You should scan. You should use the computer scan the Shakespeare's play from the beginning to the end, find out whether Brutus appear or not. And the same like Caesar. You should scan it also, and not Campania. You should scan this, and for each players you should scan these three persons: appeared or not appeared, occurs or not, presence or absence. One could grep is you cannot find this word in your English dictionary. It's a command of the Unix for computer, Unix system. You grep all of Shakespeare's plays for Brutus and Caesar. Then you strip up lines containing Campania. This is the method to find the answer of it. But it's not difficult for man to scan it linearly by your eyes, but it's not difficult for computer to do it. And then slow for large corpora. What is not the answer? Then let's see it later. Okay, now I tell you what's the structured or unstructured. We still use the Shakespeare's play as an example. Now you see this table. This match with this table. This is the play's name. Shakespeare have many players. One of the name of the player. One player's name is Antony and Cleopatra. This is first player, Antony and Cleopatra. The second is Julius Caesar, the name of the player. This is the name of player. The third name of player is the Tempest. Tempest. And the fourth player, the name of it is Hamlet. Hamlet. This is Hamlet. This is Hamlet. And the fifth is Othello. Othello. And Macbeth. All these are the name of the players. And now let's see whether Antony appeared, whether the Brutus appeared in the first play, Antony and Cleopatra. One means its presence means it contains Brutus. Brutus appeared in the first document, first player. In the first player appeared. In the second also appeared, but in the third absent. In the fifth appeared, and the next is absence. When it's absence, we use 0. It's appeared, we use 1. So the Brutus in all these six documents, just like 1 1 0 1 0 0, and the Caesar appears 1 1 0 1 1 1, and Calpurnia 1 0 1 1 1 1 1, and this means appeared or not appeared. But when we use Brutus and Caesar, but not Calpurnia, be careful, not Calpurnia. You should make the and operation, and also not operation. How to do it? Let's see how to do it as a binary. These three you can see how to Brutus and Caesar, but not Calpurnia. And Caesar we use the brown line. Not Calpurnia, we use the blue line. Be careful the blue line. Okay, how to make it? Computer, how to make it like this? You see, this is for Brutus. For Brutus, in the first one appeared 1 1 0 1 0 0. That's 1 1 0 1 0 0. And Caesar, you just 1 1 0 1 1 1, like this. And for Calpurnia, be careful. You cannot put 0 1 0 0 0 0. That's wrong. You should make it opposite. When it appeared 1, you should use it appear 0, you should use 1. When it appear 1, you should 0. And 0 0 0 0, you should use 1 1 1 1. Just the opposite to it. That means not. Just the opposite. You use this. Just the opposite to Calpurnia. Calpurnia 0 1 0 0 0 0. You should use 1 0 1 1 1 1, because it's not Calpurnia. So and not. So you make it like this. Then the result is 1 0 0 1 0. How to make it? Because it's 1 1 1. Then it's 1 1. And the second column is 1 1 0. It's 1 1 0. When it appears 0, it's 0. And the third 1 1 001, the third column. So it's 0. As it appears 0, you should make it 0. Or it's 1, 1, 1, 1. Then the result is 1. When it's 0, 0, so it's 0, 0. 0, 1, 1 make 0. 0, 1, 1 make 0. So the result is 1, 0, 0, 1, 0, 0. It means this is 1, this is 1, this is 0, this is 0, this is 1, this is 0, 0. So the 1 means the result, what you want to find it. What you want to find it. That means the 1 means the first, Antony and Cleopatra. This one. And the second, third, fourth. The fourth one means 1, 2, 3, 4. The Hamlet. These two players, the first one and the fourth one, just matched the result. So you find that only these two players, according to the just what you wanted. It's the result of what you wanted. So this when you make the information, the natural language put into like a matrix, and you cut the text to the several documents, then you make all the vocabulary, we call it terms, make it a matrix like this. We call these data structure. And as natural language is unstructured, some text, but in fact most text unstructured. In fact, it's semi-structured because many texts have the title and the paragraph and also the end note. You can consult, you can search by the title or by the paragraph or by the end note. So it's semi-structured. A structured means, the data structured means make it like this, the matrix, make it like vectors, like this. So in the computer, you put the text into the database. The first you should make the computer make it automatically, like this, like the matrix. It's easy for you to search, to consult. So we call it structured data. And this is the result. We just search it in the computer. The first player is Antony and Cleopatra act. So you find Caesar and Brutus, but without Capernaum. You see, these two appears, but without Capernaum. And in the fourth Hamlet, in the fourth actor Hamlet, and you find it also Caesar appeared and Brutus appeared, but without Capernaum, without the Caesar's wife. So it's very quickly find. Search the end from the document, and that means you get the information retrieval from the database very quickly, very easily. That's why we use structured data in the database. It's just easy for retrieval. for query to get the information quickly. Okay, but the problem is that as it make the bigger retrieval, the bigger collections of it, like you consider just there are 1 million documents. That means if we have 1 million plays, that's not Shakespeare's plays. Maybe all the you collect 1 million plays, you use it as your document, or you cut the text each 1,000 words as one document. So there are 1 million column in this table in the matrix. The column is 1 million, and if each word you find it whether appeared in the document, there are each word average you think it's 6 bytes. 6 bytes average. Just some may be longer than that, some shorter than this word. You just average 6 bytes, and the data in the documents were 6 GB, and see there are 1,500,000 distinct terms among these. What means terms? Terms, that's the word. That's the word, whether it appeared in the documents or not. The terms, there are 500,000 there. Then, what's happened? That you can find there are too many matrices has 500 billion zeros and ones. So your computer cannot bear it. Maybe too much memory. Your computer just crashed. Cannot put it on the computer's memory. Computer cannot bear it. But there is another method to make it. The matrix, because the matrix is extremely sparse, just that means a few appeared. Just like in the sand, bigger sand, there are only a few pounds there. The 1 million, maybe there are many zeros, but a few one on the matrix. So what's better represented? We can find the better way to record it. We only record the one position where the one appeared. We record it. When 0 appeared, we don't record. We just skip it. Then we can save a lot of memory, so the computer can support it. For this, because the matrix is so big, with two documents and the columns and too many 0 and 1, and it's costs a lot of memory. So we should use another representation to express it, to save the memory. And then the people created the inverted index. What is the inverted index? Let's see. for each term T, we must store a list of all documents that contain T. The document in the example before, we used Shakespeare each play as a document. Now we not use the name of the document. We just use the number of document. The document 1, document 2, document 3, document 4. We don't use the name, just use the number. The number. Identify each document. Use the number. And then, can we use fixed size arrays for this? Yes, we can. And now you see the Brutus in the number 1 document appeared. In the number 2 document number 2 appeared. And in the document 3 not appeared. These words, Brutus. And in the document 4 appeared. And in the document 11 appeared. The same Caesars in document 1 appears. And in document 2 appears. In document 3 don't appear. Absent. In the document 4 appeared. Then we just recall in which document ID appeared. So we make a table like this. It's much easier for this method to record. We call it inverted index. It saves a lot of memory compared to the matrix. If you make a matrix, you see there are at least 174 columns and also many rows there. Also, these 3 words we have 3 rows. Each words we call it a term. Terms. This is the term. This is second term. This is 3 term. Inverted index means the term plus the list. We call it the posting list. The term. This is the term. This is the posting list. Connect it is much easier instead of the matrix. We don't use matrix to express the structured data. We use the inverted index for save the memory of computer. Now, what happens if the word Caesar is added to the document 14? Okay, Caesar to the 14. You just put it inside. It's quite easy. Inverted index. First, we need variable size posting list. This is the posting list. That means this word, now we call it term. This term, Brutus, this term, appeared in which document? This is document number. The number of document. So on a disk, continuous run of posting is normal and best. In memory, can use linked list or variable length array. We just use this array. This array we call it post list. So inverted index means the term plus the posting, and it save a lot of the computer's memory compared to the matrix. That we call it posting, and we call this totally dictionary. And for each we call it a term Brutus, term Caesar, term Capital, and totally we call it a dictionary. And this array we call it posting. This totally we call it postings and postings. So then we sorted by document ID. More later on why. I tell you why. Here is sorted from the smaller to larger, to bigger. 1, 2, 4 is sorted. And we also will sorted the terms in the dictionary. Okay, now inverted index construction. How to make inverted index? We find inverted index just for save the memory of the computer. So let's see. Documents to be indexed. So you just give the documents cut it for each column and put it the number of it, such like then you make a tokenized. This is, for example, friends, Romans, countrymen, and then you make it tokenized. You make these documents, make it indexed, make it a structured, unstructured document, make it structured. So how to make it? First, the token string, tokenized. Make it a token string. So you cut each word like this: friends, Romans, countrymen. The first step, you cut it each words. Then you linguistic modules. You use your linguistic knowledge to make it find the original. For the friends, just from a friend, you use friend. And the Romans, you just use Roman. And without the capital, make the you don't use the capital alphabet, just like this. And the countryman, the original is countryman. You make it just like the word in the dictionary, like this. We call it linguistic modules. Then you make it inverted index. The index make it inverted index. The friends appeared in the number 2 document, in the number 4 document, and the Roman appears in the document number 1, document 2, and the countryman in document 13, document 16. So this is the inverted index. When you make the long text or the long document, long text cut it to several documents, and also make each word, each terms on the matrix. Then you make it as the term plus the listing, term plus each term plus its listing. These progress we call it after this class the next expression we just call it structure. You make the text structure. So it's just an expression of the database. How to you put the documents or the text, you put it in the database. In fact, you make it on the table, just in the matrix expression. We call it structure. Not like the natural language. We make it as a computer language. We call it a structure. So initial stages of text processing. first you should tokenization. Dear Jones as a state-of-the-art solution. And then you make it normalize to match, and also stemming it. This is not initial stages of text processing is not important. You just read it after the class. It's save the time also, and index steps, that's very important. Token sequence, I should put emphasis on it. You should pay attention to it. Index steps. Token sequence. So for the text, I did enact Julius Caesar. I was killed. I'd capital. Brutus killed me. So let it be with Caesar. The noble Brutus has told you Caesar was ambitious. This one text, you cut it as two parts. You cut the total text as two documents. This part is document 1, and this part is document 2. Then you from the document 1, you find each term. I is term, did is term. I did enact Julius Caesar. I was killed. The capital Brutus killed me. From here to here is document 1. So the document number is 1111 until here. And these each word, each term, now we call it a term. Each term you put from sir, this is sir, you put here and to here. Then you document 2. You make this table. This is the first step. We call it tokenize. The first step, token sequences. The sequence of pairs. So each term's pair, their document ID, document number. That's what it is. This is the first step. We make inverted index. This is the first step. Then we see the second step. First step is make term and document number. Each term compare one document number. And then we see the next step. That means sort. We sort it. And sort not only sort terms, you also sort the document number. You sort both. First, you sort the term. This is not sorted. After it is sorted, the terms like this, according to the alphabet, sorted the alphabet. This is A, B, B, C, D, E, H, I. You sorted it. You use all these terms just like dictionary. To sort it from A to Z. You sorted the terms. And each term follows document number. Each term follows its document. Some terms appeared not once, several times. For Brutus appeared 1, 2, 3, 1, 2 times, twice, and first appeared in document 1, and the second Brutus appeared in the document 2. So you sorted the term first. Then next step is after you sorted the term, like a dictionary, like your dictionary, then you put the document number here, You merged. For example, these two Brutus, you merged two Brutus as one Brutus, and the posting lines means the Brutus, first the Brutus in the number 1 document, the second in the number 2 document. You just Brutus and the frequency 2. Frequency 2, that's not important. The important is the person lists. The Brutus appeared in document 1 and in document 2. And the Brutus, the capital 1, and the Caesar, you see, there are 3 Caesars, but you can merge these in the number 2, in the document number 2, just like 1. And this Caesar, the frequency is 1. The first, the frequency is 1 because it appeared in document 1 and in document 2. In document 1 appears once, in document 2 appears twice, but we still in different documents. That's 2 means 1 in document 1, in document 2, which means 3 times. In fact, it's 2 times. In fact, it's 3 times, but in the number 2 appears twice, but we can consider it just 1 in the same document. In the same document, we just consider it 1. So in the document 2, in the document 1, the frequency is 2, not 3. And also this is the merge. Some like a cured. There are also the paired in 1 document and in 1, also in 1. That's frequency because in the same document number 1, so we can frequency just 1. And we merge it, 2 cares, just 1 care, just 1. And there are 2 because it's in different documents. In document 1, document 2, so that has frequency 2. 1 is document 1, then document 2. And words also, there are 2 words. And the first was in the document 1, the second in document 2. So what was the frequency is 2. And in the document 1, document 2. The frequency is not so important for the structure. Most important is term plus its posting lists. Connect this, joint this, we call it the inverted index. And why frequency? We will discuss later. Because it has a frequency, we can use another method to search. We use the index, converted index for the Boolean search. But sometimes we will use ranked search. We will use the frequency. We will not make explain in this chapter. Later we can make the explain. In this chapter, you just pay attention to the Boolean information retrieval model. So you just pay attention to the term plus posting list, and this is the term, and here is the posting list. posting list. Each term connect its posting list, and we call this is the inverted index. With such a method, compared to the matrix, we save a lot of computer's memory. So this we call each of these terms, and later we will tell you the pointers. The pointers, just like a needle. Just imagine that the needle in the computer point each number of the posting lists. Okay, and this is the list. This is the 1, 2. This is the list of document numbers. Means the Brutus appeared in document number 1 and in document number 2 twice. And the information retrieval system. How do we index efficiently? Well, how to index efficiently? As I told you before, that because in the matrix, the number 1 is very sparse. Mostly are number 0, so we will not use the matrix directly. We use the inverted index. Then we make the index efficiently. How much storage do we need? We need the storage as less as possible. Then we can make the search quickly, and we will avoiding the computer correction. So query processing for an inverted index. The index we just built. How do we process a query? What kind of query can we process? Our focus is, let's see the query processing and how we use the logic operator and to the algorithm. Consider processing the query. For example, if we try to find the Brutus and Caesar appears at the same document, at which document they appeared at the same time. First, you locate Brutus. You locate this Brutus in the dictionary as a term. Then retrieve its postings. Now you see the Brutus, and its postings means the Brutus appeared in number 2 document, in number 4 document, document number 8, document 16. So all these are the posting, are the Brutus, this term's posting. And then we try to find Caesar, the term Caesar, Caesar's posting. Caesar's posting means Caesar's, this word appears in document 1, document 2, document 3, document 5, and so on. And the Brutus Caesars, they have the inverted index now. Then, as we use the and in the algorithm, we should merge the two postings. This means we try to find they appeared in the same, in which document they appeared at the same time. In which document both they appears. How to do it? We make intersect the document sets. How to do it? Intersect the document sets. Let's see it. We can walk through the two postings simultaneously. The first listing. The first post list is Brutus. The second is Caesar. We can walk through the two postings simultaneously at the same time. Linear in the total number of posting entries. That means you scan the Brutus from here, from left to right. You also see the Caesar from left to right, but simultaneously. At the same time, you begin. Whether it's equal or not. This is not equal at the beginning. Caesar is 1 and Brutus is 2. That's not equal. If it's equal, then you put it to the result. Now it's not the equal. Then what we can do? Then you let the small one, the small one go first. You let the 1 go first, then to the 2. Then you compare Brutus and Caesar. These 2, that's equal. Then you put the 2 to the result. After you put the 2 to the result, and the Brutus go to 4, and the Caesar go to 3, then you compare 3 and 4. If it's equal, it's not equal. Then what's happened? You let the smaller one go first. The 3 go to the 5. Then compare 5 to 4. That's not equal. Then you let the small. 4 is small. You let the 4 go to the 8. Then you compare. You compare the 5 to 8. That's not equal. So you let the smaller go further. You let the 5 go to 8. Then you compare 8 to 8. That's equal. Then you put the 8 to the result. Then go at the same time. The Brutus go to 16. The Caesar to 13. Then you compare 13 to 32, whether it's equal. It's not equal. Then you let the smaller one go first. The 13 go to 21. Then 21 to 32. That's not equal. You let the smaller one go further to 34. Then 32 compare 34. That's not equal. Then you let the small one, 32, go to the 64. Then you compare it. It's not equal. That's the end. So there are only 2. The result is 2, and the result is 2 and 8. The result for Brutus and Caesar merged. 2, their listings merged. After they merge, the listing is 2 and 8. So this is the pseudo coding. That's not the real coding. You cannot put it like a Python language, Java language, C++ language, or on the computer. It's a pseudo coding. Just tell you how we do it. You cannot put this coding on the computer to practice it. It's a pseudo coding, and just express how we do it. We do it the merge algorithm. I just told you that you compare P1, P2. If it's equal, if P1 at the beginning, P1 not a null, not a null, and P2 is not a null, so you let it go simultaneously. You let the smaller one go first, and then you compare. If it's P1 equal document IT P2, it's if it's equal, then you put the answer. You put the answer, the P1, and then P1, P2 go further. If you put the P1 to new P1, P2 to new P2, and then they go. If the P1 is smaller than the P2, let the P1 go first. Then, if not, let the P2 go first. When it's equal, then you put it to the end. That's the merge. That's the merge method. I just show you before. Now it's use the pseudocoding to express the method. Okay, Boolean queries, exact match. The Boolean retrieval model is being able to answer a query. That is a Boolean expression. Boolean queries usually use three operators, and, or, and not, to join query terms, to join the inverted index. For each document as a set of words is precision document matches conditions or not. This is the simplest model to build an information retrieval system on. But the primary commercial retrieval tool, we use the Boolean queries for 3 decades. But now, as the website appeared after 1992, many people used to use the search engine on the website. But there are still many search systems still use Boolean, because the Boolean search can make it accurate and get good precision, but not a good recall. Maybe you use the web search several times, you can get more recalls. And we use the Boolean search, called email search, library catalog search, and your MacBook's Spotlight search. And as the Boolean search, Boolean queries only 3 operators. You see, and, or, and not. It's not enough. It's not enough. So we also use a proximity operator besides these 2 operators. The people also created many other operators besides and, or, and not, such like Westlaw. That's a commercial database, especially for lawyers, and for paralegal. And this is largest commercial legal search service, Westlaw, for example. And started 1975, ranked added 1992. New Federal Search added 2010. And this you should subscribe and pay for it, Westlaw. In America, many attorneys and lawyers use it every day. The tens of terabytes, 700,000 users. and there are majority of users still use Boolean queries. Nowadays, the West law have both Boolean queries and also the website queries, the natural language queries. Nowadays, you also can use a chat GPT queries, and it's quite according to the natural language. You also can use the chat GPT and translate it to the Boolean language. You just use your natural language, human natural language, and let ChatGPT translate it to the Boolean queries. It's very easy to do that. You can try it. Anyway, now let's see. The people find some proximity operators besides and or not, such like this. For example, in the query there are other operators. What is the statute of limitation in cases involving the Federal Tort Claims Act? If you wanted to search this sentence, you can put it in the Westlaw database query. You use limit, and you use the exclamation mark, and that means the wildcard. It's a limitation. It's use limit, and after limit, you can use Asian or A8, something like that. Wildcard. This exclamation mark. Just it's exclamation mark. Limit, after limit, the exclamation mark, just use it as a wildcard. And 3 means within 3 words. Within 3 words, you can find limit. Limit within 3 months. And a statute action. /s means you must find the statute action in the same sentence. /s means the same sentence. This is another operator. And the federal /2 means in the 2 words, total 3 within 3 words, and the claim. You use this query, you can search it accurately. So there are like exclamation mark as the operator, the / as the operator here. And another example query. I just show you that they created a new operator to expand the and or not, such like requirements for disabled people to be able to access a workplace. You try to find this word from the database. You can put it like disable exclamation mark, exclamation ed. So you can put ed or e, disable or disabled. So exclamation mark means the wildcard, and /p means at the same paragraph, and this access also exclamation mark means wildcard. /s means the same sentence. Work hyphen site. Hyphen is also the operator, and the work hyphen place. That means That means you can, without this halving, you can work at the space site, and also you can join it together work site like this. This this hyphen is also operator, and you note that space disjunction or not a junction. So all these new operators, we call it proximity operators. We we often use the operators like and or not, and now we add many proximity operators, make the query improve the queries. So that's quite not like the web search. You should have a professional skill. Some skill maybe after training you get it, or you can learn it by self-taught. Many professional searchers still like Boolean search because it can search quickly and give you a good precision. But that means it actually works better. Sometimes you use the natural language nowadays is also better. You use ChatGPT cooperate with the search engine. So this is the exercise adapted module for the questions. How to do it? You just after the class you try it. We will not make it at the classroom. After the class you try. Okay, and I tell you how to do the end module, but you think it over how to do the or, operator or. When you use end, it make inverted index smaller, and when you make or, it make it longer than the small term. You can try it. And not you use the operator not. You should use each the number 1 0 just convert. Then you make an end. When the not appeared, first you make the number convert. When 1 you becomes 0, 0 becomes 1. Then you make end. That means the not. And can always merge it in linear time. Linear in what? Can we do better? Yes, we can use it better. Just think it after the class. And query optimization. What the best order? Here we pay attention to the order. What is the best order for query precision? Consider a query that is end of n terms. These 3 terms, Brutus, Caesar, Caponia. For each of the n terms, get its postings, then end them together. If we end these three terms, the term Brutus with its posting list, the Brutus appeared in document 2, document 4, document 8. And the Caponia, Caesar's wife, Caponia, appeared only in document 13, document 16. How you make it easier? How to make it save the time? If you make Brutus and Caesar's first, it's not saved. It doesn't save the time. You compare these long list, it costs a lot of time. But if you change it, you make it compare the Brutus to the Caponia. Caponia is the shortest list port. Then you merge these two. Then the result less or equal the Caponia's long length. The length is only 2. Only the length only 2. The length is less 2 or less than the 2. Then you merge Caesar as quickly. So if you put the small length posting first, then you can make it quickly and save a lot of time, and also save the computer's memory. In precision order, increasing frequency, start with smallest. So you should start with smallest set, then keep cutting further. So you should change. Don't make Brutus Caesar first. You can choose the Caponia because it's the smallest set. You make it merged to Brutus or merged to Caesar first. That is why we kept the document frequency in dictionary. Start with smallest, then keep cutting further. So keep document frequency for that you can find which is the smallest set. Which one is the smallest set? Easy. So this is exercise. This is the exercise for after the class you can do it. This is rather complex. Tangerine or trees and marmalade or skies and kaleidoscope or eyes. You make the terms like this, and if it's frequency, each eye is a frequency like this. This is frequency like kaleidoscope frequency like this. You make the smallest first, which is the smallest thinking after class. And the merge general optimization. For example, Madding or crowd and ignore strive get the documents frequencies for all terms. Then you estimate the size of each all by the sum of its documented frequencies. Process in increasing order of all sizes. That's also you can make it after the class. This is just a rather difficult exercise. You do it after this class. If we at first you had better think it by yourself. If you cannot think it out, you can see the hint. Begin with the case of a Boolean formula here. Then you can find the answer. Okay. Thank you for listening, boys and girls. Thank you very much. Hope you success in your career and the examination also. Thank you for listening.